Okay, so hello everyone, and welcome to our second Aviva Process Simulation training session. Thank you for joining us today. My name is Bruna Giron. I am Academic Success Manager at Aviva, and with me is Richard Pelletier, our Principal Customer Support Engineering. So before I hand over the presentation to Richard, I kindly request that you keep your microphones muted during all the training sessions. And if you have any questions, please feel free to type them in the chat, and we will allocate some time at the end of the presentation to address them. Furthermore, to those who have not yet the chance, I invited you to participate in our academic competition. This is a fantastic opportunity to improve your simulation skills, enhance your CV, and have the chance to win some prizes. I will share the registration link in the chat in a few minutes, okay? Richard, thank you so much again, and I pass the floor for you.
All right, thank you, Bruna. I'm going to share my screen, then we'll get started. Okay, so yesterday for session 1, we covered a lot of the basic concepts. Due to how much content we were trying to cover, we were unable to get to one of the last topics I wanted to cover, which was just on some basic outputting capabilities within the software. This isn't going to be all the different ways you can get output, but it's just some of the ways that I haven't already talked about and I wanted to specifically point out. So we're going to start with that today, and then we're going to move into session 2. And session 2 today is going to be mostly focused on the concept of fluids, which are models that store all of your component and thermo selections. And then we're going to talk about the different modes of operation and concerns related to switching between those different modes. So that's going to be the focus of today's session. All right, so to start off, let's talk about those outputting capabilities that I wanted to point out. So one of the main things about Aviva Process Simulation is that anywhere you go to enter information is usually where you go to get your results. Right, and since the program is constantly solving, whenever you make a change, you instantly see the change take effect and you see your results basically wherever you're entering your information and elsewhere throughout the simulation. Right, so when I come into this mini property inspector and I change a value here, and I see mass flow rate update, that's because the program has already run, it's already solved, and it's already updating all the different calculated information throughout the entire simulation with the updated results. So this is an output. This is a result that I'm looking at. All right, so I'm getting my output in the same area that I'm also using to do data entry. And this is throughout everywhere. So we talked about this is the mini property inspector, but there's also the full property inspector for individual models. There's the full property inspector for an entire simulation, right? So this is for all the models in your simulation. There's other areas within the software where you can do data entry and get results, such as the areas over here with the simulation manager and so forth. All right, so now we're going to talk about a couple of other things that you can do to get your output. One of them we saw yesterday was variable reference. All you have to do is open up one of the property inspectors and then find the property of interest, drag and drop it onto the canvas. And now you'll be able to see your result on the canvas as you make changes to the simulation. And what's nice about this is, as you can see, the spec box is included with these. So this is a locked parameter. I can't change the spec status, but if I were to use one that's not locked, you can see I can check and uncheck this as I desire. So if I put on key variable references throughout my simulation, such as some of the things that you're seeing here on the canvas for this simulation, I'm able to quickly and easily go from different points of interest, swap between different specs, change values, and then see the difference on those changed values back throughout the rest of the simulation. Right, so this is one of the easier ways to get output out of the software. Another way of getting output that we didn't cover is a table model. So I have a table on the canvas already. That's this icon right here. When I double click on it, it shows me a table of results. In this case, I'm looking at stream S8, and I'm looking at these particular results that it's showing me. And so it's just the pressure in this case and some composition information. But I can create these tables for any models and for any properties that I want to look at and in whatever units of measure that I desire. So the easiest way to create this table is to find the object that you're trying to create the output for, whether that's your source models or all of your streams or maybe all the drums in your simulation, whatever the model ends up being, right click on the model, go down to where it says table, and then you're going to have the option to either add the individual model that you've selected, so in this case, stream S1, or all of the same type of model. So in this case, it would be all process stream models to an existing table. So I have some tables already, or add it to a new table. And so I can come through and I can say, I want to add all my process streams to a new table. Click this. I now have a new table on the canvas. And when I open it up, I can see, expand this so we can see it easier. I can see all the different properties that it's reporting for these streams, and I can see all the streams in my simulation are in this table. So it's a quick and easy way to get an output of all my stream properties. Right? And we can do this with any model, right? So this could be all the properties for all my drums, all the properties for all my valves, and so forth, right? Now, if I want to change the units of measure in this table, these are linked to the selection up here for the unit of measure slate. So I can't just click this and change them. This is one of the few areas where you don't have the ability to just click and change. You have to pick a slate that has the units of measure that you want to see. And then you can click the little refresh button down here. And you can see now it's in the units that I desire. And it's converted all the values over to the correct values. All right. Another thing that you can do with these table models is that if you have a property that is specified, so if I come into this stream here, this stream S1, I can see molar flow rate is specified. Right. So if I find that variable here, and I'll see that it's specified if I hover over this, it tells me it's specified, versus this, which if I hover over, it doesn't tell me it's specified. All right. But if it's specified, I can actually change this value right from the table. So maybe I change this to 5,000. I hit enter, and now my entire simulation runs, and this table updates with the new results using 5,000 pound moles an hour. All right, so this table can be used for both output as well as inputting capabilities for you to be able to make changes right from here and see how those changes take effect within the entire simulation. And then another thing that you can do with this table, and this is good for just about any type of window like this. If you see a gear icon down in the bottom right, this is usually to open up different configuration options. So in this case, when I click the gear icon here, it opens up a couple options here, as well as some options up here up on top of the toolbar. All right, and now if I select a column or a row, I have options over here where I can add more columns or rows, delete columns or rows, and I can move things around. Right, so maybe I want to move this to the top. Right, maybe I want to move this stream all the way to the left. Right, I can also delete this. Let's say now that I've deleted it, maybe I want to add it back in. So I'll add a new column here. And what I can do is now that I have this new column, I can type in the name of the model that I want to add here. And I could type S2 for the stream that I just deleted, right? But I could also do something like gas feed, right? By typing gas feed, that's a model, just like the streams. And so even though it doesn't have a lot of these properties, the properties that it does have are being filled in. right? So it has a mass flow rate, it has a molar flow rate, it has a volumetric flow rate. And so you can see results for that model as well. So you can mix and match different model types and different properties, right? So this is one convenient way to create a table. And now if I want to get this outside of the software, I can click this Generate Excel Report button, and it'll come up and allow me to export this to an Excel file. Just give this a second. There we go. And now I can see my information in a nice, clean Excel report. So that's one way of getting my information outside of the software is through this export option through the table. Another way that you can create stream property reports is if you go to the SimCentral example folders over here, and you go to the simulations folder that I showed you guys yesterday, there's a tools and reports folder here. And inside here, there's a process.stream report. So this is good for the process model library, right? And if I double click and open this, this uses our Excel add-in capability, but it's a report that's already been formatted that uses that Excel add-in capability to quickly generate an Excel report for stream information within a file. So what I can do, we're going to talk more about the Excel add-in on Thursday, so you'll see this in more detail then. But I can come to this tab, which should appear in your Excel after installing Aviva Process Simulation. I can click Set Default, and I can choose a simulation file from my simulation repository. So the file I have open right now is Pro1C. I'll select that. I click Set Default. Now my table is going to start to populate with information. And so you can see I have a table with just a couple properties and all my streams from that simulation. I can actually select this here and change what report is being shown. And so there's a couple of different reports here that give different levels of detail and information. Right. And if I go down to this detailed one, I can actually get a report that has component-specific information. But you'll notice this component information, it tells us you need to update the fluid components. So the file here, this Excel file, doesn't know what the components are just yet. So you have to come over to this fluid tab. Bruna, if you're on the call, could you please admit people into the call?
Yeah, I am doing this.
Okay, sorry,
For
there's
some
a few
reason
there.
there is some for some reason it is still with a message that it's at the meeting, and
Okay.
they are not entering. I don't know why.
Okay, then no problem. So we come to this fluid tab, and what we can do is it tells you up here, copy the component list from the fluid, which we're going to talk about fluids real soon, right? We copy the component list from the fluid and paste it into this table starting on cell A2, which is the cell that says name. All right, so if we come over to our file, we go to our fluid. We go to the component list. There's a little bar in front here, which you can't really see, but you can select it and you can click and drag. You can highlight all these, do a Control-C to copy, and then you can come back to the Excel file, Control-V, paste. And you can see it's pasted over my component list with all of the component information, as well as the headers for each of the columns. Now when I come back to the stream, it's populating all of my component data. You can see that here. So this table, this tool, this spreadsheet gives you a quick and easy way of creating a stream report file for any simulation file that you have within the software. And then you have options up here. You can switch between different units of measure. And there's a couple of other features that we'll talk about when we talk about the Excel add-in. You can see some of the other things that you can do with this. I'm not going to spend time talking about it, but there are ways of creating your own report through here. All right, there we go. So you can create your own report that you would then select from here by going to the report configuration area. You type in the name of your report in the next blank cell in this row 9, and then you start typing in the properties itself here. The only thing you have to be careful of is that anything that's a component-specific property, such as compositions, they have very specific formatting up here. And so if you want to learn more about that formatting, you can go to the FAQs. And if you go down to, I think it's question 8. Yep, this one here, question 8. It'll tell you how to set it up for a component array. All right, how to set up the line so that it properly pulls the correct information. All right, but you can't create your own custom report. Okay, so coming back to the software, there's one more type of output that I want to show you real quick, and it's called a profile plot. So over here, I have a couple profiles. They're linked to this column, but they don't have to be for just columns. They can be for anything that has array data, such as composition information and so forth. Anything like, let's say you have a plug flow reactor that has number of tubes, right? Or you have a rigorous heat exchanger or something along those lines that has like numerous elements, right? Those will often create arrays of results. So this is a great way to visualize those results because it's going to plot those things against the array element itself. So the number of segments or the number of trays or the number of components. And then you can kind of see that information very, very easily. So if I open this up and I look at this plot here, it's showing me for that column the vapor flow rate from tray to tray and the liquid flow rate from tray to tray. And these are the different trays, right? So this is tray 1's value, tray 2's value, tray 3, tray 4, all the way up. And what's nice about this is we can actually invert this. So we come in here, if we flip it, and now we're actually looking at it as if we're looking from top down on the column. So the number's a little off here. Just give me a second. It resets it there after flipping it. There we go. So we can kind of visualize it as if we're looking at an actual column here, see the results from one tray to the next. And what's nice about these profile plots is that they, once you set them up just like a table, right? It's an icon, it's on the canvas, it updates whenever the results are updating. And so let's say you're running dynamics. When you're running in dynamics, you have results changing constantly over time. This plot will also change dynamically as it's running. So you can actually see these lines waving about as the run runs dynamically. It's pretty interesting. So it's a pretty good way of visualizing that type of output. The way that you go about setting this up, you go to the Tools menu. And by the way, you can add a table from the tools as well as variable references, but the ways that I showed you are easier to add them than by starting with one of these from a blank slate. Right. For a profile plot, you come over here, you drag and drop the profile onto the canvas. And the first thing you want to do is you want to find the variables of interest. So let's repeat this just to make it easy. Right, so we're going to look for the vapor flow rate from tray to tray. Now, we're not trying to pick every single one of these. We want the array as a whole. So we're going to drag the array and we're going to put it onto the profile plot. And when we do that, we can see it's automatically plotted them and set up the profile plot so that the first profile is using that V array. Right, now, if we do this again with another property, let's say we wanted to add the liquid here. We drag and we drop it. What it does is it actually appends it to the existing profile, right? Every line that we see on this plot is a separate profile, right? So if we want 2 different lines, we need 2 different profiles. And so there's a couple different levels in here in this one little section here. The first level creates new profiles, while the second level actually creates more points in that profile. And so we just have a second set of points in this same profile. That's not what we want. Well, in reality, what we want is a second profile. And what we can do is we can drag and drop it into there. And now we have our second line. All right, so it's an easy way to set this up is by using these drag and drop options. You just have to be careful when you start to make the second or more plots on your graph. All right, I don't want to spend too much more time on any of that, so we're going to call it here and we'll move on to our session 2 topics, which are going to be the fluids to start. So let me close this and we're going to open up a new simulation. All right, when you have a new, when you're creating a new simulation, most likely when you start, you put down the source on the canvas and you're going to want to change the starting fluid that the source is using. So in this case, the starting fluid that this source uses in the process model library is this def fluid. That's this one here. And all it is air, right? If we look at the composition, we can see it's just 21% oxygen, 71% nitrogen. All right, so it's just air. All right, now the whole reason why we use fluids to start that are predefined is so that way when we add the source onto the canvas, we're square and we're solid. All right, one of the core design philosophies of the software in general is that we are always square and solve when we drag and drop models onto the canvas and connect them together. Right, so I drag this next model, I connect it. I should expect to be square and solid, right? And so everything about the way that the models are set up, meaning what things are selected, what values are specified, that's all there to support making sure you are square and solved when you're building it out, right? And so that's the core design philosophy. But just because we put stuff there in place for many of these different selections and property values doesn't mean that that's something that you're going to want to use. And for most users, air is not going to be the fluid. So now you need to create your own fluid. You can do this one of two ways. You can either find an existing fluid, copy it, and then paste it and edit it, or you can right-click in some empty space in one of the model libraries, and there will be an option that says Create New Fluid. All right, now we're going to go down the path of creating a new fluid from scratch and seeing this, but before we do that, I want to talk about this folder here, this tab that we're in. Each one of these tabs is a different model library, and when we go on most of them, you see models in those model libraries. However, the bottom tab is always going to be what's referred to as the simulation specific model library. So this is a blank model library that is used only in the simulation that you have open. And it's a place for you to put all of your custom models that you plan on using within that simulation. Your custom models can be everything from fluids that you have to create so that you can use them in your files, performance curves that get used in pumps or compressors, valves, etc. Or they could be customizations of equipment models or submodels that you are using to help build out your flow sheet, right? So a good example of a custom equipment model might be you take this drum and you add some kind of additional equation that the drum isn't already using or calculating, some additional property you need to calculate for, right? So you could copy this, you can paste it into here, you can edit this one and then use this on the canvas, right? If you're using reactors, something that's common with reactors is to create a reaction submodel. And so you'll have something that looks like one of these down here. That's a submodel. It's a set of calculations for a very specific purpose, in this case, the reactions, right? And you'll have a reaction submodel over here that's stored in here. Now, why do you put these things in this simulation specific model library? The reason why you want to put all your customizations into here, as opposed to one of these other tabs, or even a brand new model library that you've created, is because when you export this simulation to a SimX file, anything put into this simulation-specific model library is going to be stored in the SimX file, right? So what that means is that now you've created that SimX file, you give it to someone else, especially for deliverables for this competition. They import the SimX file, they're going to have everything they need to run your file. If you put your customizations in a different file, a different library, or even a custom library that you've created, that's only on your machine, right? So when you export to a SimX file, that information is not going to be retained, and your simulation is actually going to be pointing towards that specific model library for the custom model, right? Remember, when we look at these models up here, they tell you this is the source model coming from the process model library, right? And so the fluid here, this is the fluid coming from the process model library. When we create our new fluid and we put it into the simulation, it's going to say models.fluid1, right? Because it's fluid1 coming from the simulation specific model library, right? So we want to make sure we put our customizations in here so it's stored in the SimX. Now, quickly, we're not going to be talking about library management right now. That's actually something we'll talk about tomorrow. But what if you do store it somewhere else? You have the ability to create libx file, right, through model writing, right? So you can export the library and create a libx file that you can also send to people with the SimX, and then they would import the libx so that they have access to your customizations, and then they would import the SimX so that the SimX points to the custom library that they just imported and gets the proper information from there. All right, so that's how it would work if you put these customizations in a different model library. Right, but you want to store everything in your simulation specific model library, preferably. Okay, now that you've created these new fluids, you need to set them up with the component and thermo selections. And so we're going to go through setting up this new fluid that we created from scratch so that it has the components and the thermo information that we need. Right, so we can double click on the fluid, or we can right click and click edit, and it opens up what we refer to as the fluid editor window. This is the window that we use to edit any fluid model. It has the same general structure to the way that it's set up for every single fluid, right? But this is a specific window, editor window, that's only for fluids. If you went into the editor window for a model, like a pipe, you can see it's different, right? It's different information set up differently. If you go into the model editor for a performance curve, again, it's set up differently, right? It looks different, right? So each of these different types of models have a different editor window. That's why when you right click to create the fluid, you see these other options. They have different structures to the way that they go about being set up. So we're specifically talking about creating the fluid type of model, and this is the fluid editor window that we're going to be reviewing. All right. Now, in this window, the first thing you want to do is start with the general section, which is going to allow you to give your fluid a name. So this is going to be my demo fluid. All right, so that's the name. I can also give a description. Now, descriptions are very useful in this software because anywhere, not even just here in the fluid editor, but anywhere where you have the ability to put a description, it often gets associated with a pop-up that comes up when you hover over whatever the thing is, right? So if I give a description here, this is my description. It is being used to help explain what this fluid model is, right? So this is my description, right? When I hover over this fluid, that's what I see, right? So when I hover over a fluid that's already created, like these ones over here, and I see this information pop up, that tells me what type of fluid it is, what phases it supports, what's the thermo method it's using, what components it's using. This is all because someone took the time to type in a description with all this information in the way the fluid's designed. All right, so this is useful, so that way you can inform other people what exactly they're looking at without them having to delve into the model itself and get a better understanding of what's going on. Again, these descriptions are everywhere, though. Let's take this window here. When I hover over this variable and it tells me that it's the source forward mass flow, right? So the mass flow rate, all right, it's because there's a description field where this variable set up in the source model and someone wrote that into the field, right? When I hover over this and it says elevations, I'm not only seeing a description of what this parameter means, but what the different options are, what they mean, and how to use this parameter properly. And that's all because someone took the time to put this description information in. And so you'll see this throughout the software, everywhere in the software. These pop-ups are oftentimes associated with someone providing meaningful descriptions. It's a good idea for you to also provide those whenever you have the option. All right. Now, the next thing in this area, and this is really the main reason why you start with this general section, is this selection of thermotype. By default, it's going to be set to compositional. A compositional fluid is one that's defined by pure library components. So components like water, methane, ethanol, right? Those are all pure library components. All right, and by rigorous thermodynamic methods such as SRK, Peng-Robinson, NRTL, so forth, right? That's what it means to be defined as a compositional fluid. However, there are other types of fluids that you can define, right? So we're going to take one example, incompressible liquid, right? If I define a fluid as an incompressible liquid, I don't define it using library components, even though there are components that would create incompressible liquids, right? And I don't define it using rigorous thermodynamic methods. Instead, what I have are bulk properties that I'm entering that define how the fluid behaves when it's used in the simulation, right? So an incompressible liquid is going to assume that you're always in a liquid state, and it's going to assume that that liquid behaves based on the properties that are defined in this section here. Notice, even if I expand these other areas here, there's nowhere where I define a component list, pick a rigorous thermodynamic method, set a phase designation for it to consider, none of that. This is a different way of defining your fluid and how it behaves, right? So the first selection here of picking the type is important because that's going to change the information that you're required to enter throughout the rest of the fluid editor. Right? Now we're going to focus on compositional fluids. That's the main goal here, is to create compositional fluids. All right, but if you have a need, you can always change that and make it a different type of definition. All right, so with a compositional fluid, the two main areas are this methods area and your component list. So we're going to start with the component list, even though it's further down in the screen, right? The component list is where you're going to go to pick your components. So we're going to pick some simple components here. We're going to do methane, ethane, propane, and as you can see, what I'm doing is I'm typing these components into here and I'm hitting enter, or this plus sign, and it's adding it to the list. This list here is the list of components that are actually being used when I use this fluid, right? So if I put this fluid onto the source, it's not going to have water. It's not going to have any other components that I don't see listed here. It's only going to have these three components, right? Because that's what I'm telling it to use, all right? So when you're setting this up, the most important thing to remember is that if you need a component, it needs to be entered here in this list. Right now, what happens when you type something in, say isobutene, and it comes back and it tells you it can't find it? right? So if for some reason it can't find a component, you can come to this section here where it says Component Browser. In this area here, you're going to see a list of all the components available to you within the software, right? And you can search this list. See, this little scroll bar here doesn't move very much, right? You can search this list by any one of the fields up here at the top. So put your cursor up here and start typing in what you're searching for. Now, the issue with this here, not finding isobutane, is the fact that this field only searches the formula and library name fields. So when I typed isobutane and it tells me it can't find it, it's because it can't find it in this field here, right? Isobutane with an E at the end, see, it can't find it, right? So isobutane is the full name of the component. If I typed it in this field, it would have found it just fine. All right, so you have to be aware of that with the search. It is searching these two columns here. When you're searching and you're using this component browser, you can search any field you want. And you saw as I was typing, and again, I'll do it one more time. I'll do it in this field here. As I'm typing, the list is being filtered automatically by components that match what I'm typing. Right? And you'll notice it goes with the embedded search by default. Right? So it doesn't have to start with isobutane to find it. When I find the component that I'm interested in, I click the little plus sign in the front and it adds it up to my component list. All right. So the only way to add it up is to click this plus sign, right? That's important. All right. And until it's in this list, you're not actually using it. Once you find all the components you're interested in, and they're all defined in this list, you can go through and start entering a starting composition for this. Now you'll notice it defaults with the first component being 100% and everything else being 0. Right? So you can leave it like that, but 100% of the first component may not always be reasonable. What you're trying to do in this field is provide a composition that when you place the fluid onto the source, ensures you are square and solid, right? So you want to provide a reasonable starting composition. A lot of times this ends up being whatever your feed composition information is. All right. So if you know your feed composition is certain values, you can put those in here and you can use that as your starting composition. But what if you're using this fluid over and over again across many sources? Every source might have a different composition. So you're not going to be able to satisfy every single source with just one list of composition. So the main goal is just to make sure you have something that is reasonable, something that's going to help ensure that it's square and solved when you put it into effect. All right. So I'm going to start off with just equal molar values. All right. And that should be sufficient. Now, this is going to be it in terms of what I'm going to do with this file, but I do want to show you one more type of component that you can add that's not a library component. So this goes into a little bit more of refining, and that might not be used in this project, but I do want to mention it maybe for future projects. We have the ability to add individual petroleum cuts by clicking on this button, which will add a petro component to the list. A petro component is one that's defined by the properties you see in these columns here, right? And you need 2 of the 3, or preferably all 3, to be defined in order to satisfy the definition of this component, right? So if I come over here and I provide some values, and once I provide 2 of the 3 values, you can see this turns green, and now this is satisfied. And what happens is the program takes this information and is able to characterize all of the other component properties for this one component and populate out everything else that would normally be found for all the different component properties. Right. So the more of this that we provide, the less that the program has to calculate. So if I knew a molecular weight, instead of it having to calculate a molecular weight based off of these two values, I might want to provide that. But I only need 2 of these 3 to satisfy the requirements. Right now, this is how you would enter an individual petroleum component, which is typically a single cut of a larger distillation assay. Right, so a distillation assay is usually something that's defined by percent distilled over temperature. And that's a table of data that when you enter it, it will then get broken down into a number of components, usually something in the range of like 50 or more components. And each one of those components is going to be representative of a single section of that assay, a single boiling range, right? And so this is just representative of one of those boiling ranges of an entire assay. So if you had a full thing of assay data, you would need to enter multiple of these petro components in order to sort of satisfy all of the assay information. So this is right now the only way that we can enter in distillation curve information is by using individual assay points. But in the future, we are looking to add assay support. We're just not there yet. So in the future, we will hopefully see additions either to this window or in some other way where you can enter in a distillation curve and have it break down into individual petro components for you. All right, so wanted to take a minute or two to cover that, mostly for potential future projects. Okay? So we're going to delete this. We're not going to have it in the demo moving forward. All right, so now our component list is correct. We want to move on and add our thermo selections. So we're going to come over to this methods section. And the first thing we're going to want to do is pick a rigorous thermodynamic method here. Now you can see there are many choices that are available to you. And picking a thermo method, while simple, right? It's easy for me to just go and pick SRK. This could potentially have the biggest impact on the results in your simulation. So this is one of the most important decisions you're going to make during your entire simulation process, right? Because whatever you pick here is going to dictate the accuracy of your results moving forward wherever you're using this fluid. So you need to make sure that you pick a method that is appropriate for the system that you are trying to simulate. How do you know what's appropriate? Well, you start with your component list, right? That's why I started down here and not up here, right? Because we need to know what components we have and what kind of components are they. These are light hydrocarbons. And so there's numerous methods here that are sufficient for light hydrocarbon components. But if I had these light hydrocarbon components and maybe water, that adds a little bit more complexity. Maybe I have these light hydrocarbon components, water, and some chemical components. That adds even more complexity. And so we start to get to a point where I have to pick very specific methods for those types of components. Otherwise, my results aren't going to be accurate. All right. So when you're trying to determine what is the most appropriate thermo method to select, there are a little bit of resources that are available to you. All right, so the first thing first, you can come to the help documentation we talked about yesterday. And there is a whole section over here for thermodynamics. And when you expand it, you can either browse by type of thermo method, which is typically going to be like equations of states, liquid activity methods, generalized correlations. And so these are going to encompass multiple different selections in this list, right? So for example, SRK, Peng-Robinson, SRK-M, Peng-Robinson-M, SRK H, even predictive SRK, these are all what we would call equations of state, right? So when we look at this help documentation, it's this section here that's sort of talking about all those collectively, right? Now, each one of those is unique. They have their own individual things about them. But this group of thermo selections is called an equation of state, right? And then we have others that are called liquid activity methods and others that are called generalized correlations. So each type is specific for different applications. And so you need to familiarize yourself with the types of components you have, as well as what are your typical operating conditions. What kind of temperatures and pressures are you looking at? What kind of compositions are you looking at for the components you have? Because if you have something that has a whole lot of a certain component that's maybe non-ideal or very polar, that's going to dictate a different thermal method than others. And so these help documents here are going to help you get a better feel of what the different methods are used for, their applicability, right? So like this one here, NRTL, liquid activity method, works well for strongly non-ideal mixtures and for partially immiscible systems. All right, so every one of these methods is going to have some kind of recommendation like this that you can reference. And you're going to want to go through and try to understand what is going to be the best selection for your system. All right, so it's a very important decision to make when you're making this selection here, even though it's one of the quicker and easier things to do within software. Another resource that you have available is to call us at tech support. So if you call us and you call the support hotline for SimSci, we'd be happy to give you a thermal recommendation for whatever system of components that you're using. Another resource may be the competition organizers. You can refer to them as the ones that put together the problem and ask them for a thermal recommendation if it's not already given. It may already be given in the academic competition description information, right? So always check the resources that have been supplied to you. It may tell you use SRK, use NRTL, okay? Now, these different thermal methods, when you make a selection here, depending on the type of thermal selection that you make, right, an equation of state versus liquid activity method versus generalized correlation, going to have different modification options down here. We're not going to spend a ton of time on this because this is more for academic use. So I'm assuming that you're not going to need to touch any of these modifications. You're just going to pick an overall method, and that should be sufficient. However, if you ever did need to make modifications to specific property calculations or what property values are being utilized, you have different modification options for every single thermal method in this list that are unique to that method or that type of method. All right, so you can go through these selections and you can pick and modify things accordingly. All right. Now, the last section that we need to cover here is the phase designation. There's a pull down here, and you see it's marked as red, where we have to pick what phases to consider when using this fluid. And this is important because you're trying to gauge and kind of balance your level of accuracy in terms of the results that you get out of the software with the performance out of the software as well. Usually the farther down this list you go, the more accurate your results are going to be, depending on if it's applicable, right, for your system, right? But the more complex the calculations become, and so therefore the more bogged down the simulation can become, and the more time it takes for it to process things when it's running calculations. All right, so you always want to weigh: do I need it to be more accurate, or do I need better performance out of the software? Now, generally speaking, computers are pretty good. They can handle quite a bit. You can go pretty far down on this list with a smaller file and a not very complicated simulation or fluid and get fairly good performance out of the software without even batting an eye. It's when you start to get into very large simulations or fluids with very thermodynamically complex systems. Maybe you're using one of these more advanced thermo methods in this list, and you have a bunch of non-ideal components. When you go down and you pick VLWE or VLLE, that's going to add a lot more intensive, calculations to the system and make it harder for the program to just kind of chug through all the calculations, right? And so that's when you have to start to make the decision: do I go with something simpler, or do I go with them more complex for the more accurate results? All right, and there are things we're going to talk about in just a second where you can change the fluid, the phase designation on the fly, depending on if you need to introduce more accuracy in certain sections versus less. All right, so typically in most systems, you're going to pick VLE, and that's telling the program that you could have a vapor phase, you could have a liquid phase. Doesn't necessarily mean it's always going to be one or the other. It could be both, and mixed, or whatever the case may be, right? So that's typically the most common approach. If you pick vapor or liquid only, you are telling the program to only consider those phases. And so if you ever reach a point where, let's say you're vapor only and there's liquid that's formed within your simulation somewhere based on the process conditions, it's going to fail to solve. It's going to give you inaccurate information and unconverged solution, right? So you have to be careful, what you pick, to make sure that it is all encompassing of what you might have within your system. For these more complex ones, it adds a third phase that gets considered. For VLLE, you have a secondary liquid phase, which could be any other component that's not immiscible in the primary liquid, right? So you could have, ethanol, water, type of thing that creates maybe two separate liquid phases. That's potentially something that could happen, right? And so you choose VLLE, right? VLWE is where water gets treated as a separate pure water decant type of phase. All right, and what ends up happening here is when it does all the equilibrium calculations, water will saturate the vapor phase, the water will saturate the liquid phase, and then any excess water that goes beyond the saturation point of the other phases is treated as a separate liquid product that's just pure water. All right, and so we call that water decant effectively, right? And so that's what this is doing here, right? So if you have a lot of water in your system, typically you're going to end up picking this. If you have potential of multiple liquid phases, you're going to typically pick this. But if you pick VLE, even if you have those potentialities, the secondary liquid or the excess water just travels with the primary liquid. So it's still going to go mostly in all the same areas. It's just that when it comes to separation, it's not going to properly separate the different liquids from one another because you don't have anything separating the two different liquid phases, right? So typically what ends up happening is you do most of your calculations in VLE, and then you switch to VLWE, or you switch to VLLE to do more rigorous separation in specific models like the separator model, which is a three-phase separation model, or the condenser on a column, which can do three-phase separation. Models like that, where three-phase separation can occur, will typically be the point at which you switch to a three-phase designation. Otherwise, you just keep it as VLE because, a pipe, for example, all the flows that comes in is coming out at the same point. And so all the vapors together, all the liquids together, it doesn't matter. A drum even, all the vapor is going to go overhead, all the liquid's going to come out the bottom. It doesn't matter if it's two separate liquid phases or not. All right, so you have to think about these different considerations when you're making these decisions here and setting up your fluid. Right. Typically, and I suspect for this example, this competition simulation, you're going to pick your overall thermal method and your VLE probably for your phases, and you're just going to be done at that point. And there's no more modifications you're going to do, and there's no more other considerations that you need to do. Right? But in the real world, if you were doing this for a project at a company, you'd have to think about all these things that I've been talking about. And so that's why I spent a little bit of time talking about this. It's important to understand these impacts and the significance of the simulation process when it comes to thermo and phase calculations. All right. So now I have my thermo information set, my phases are set, my components are set. I'm done with setting up my fluid. So I can close this out, and now I can take my fluid and I can drag and drop it onto my source Now, before I do that, I want to point this window right here. Watch this field, right? I can drag and drop it onto my source. And now my source is using that fluid that I have created in this source model. And if I expand the component list, I can see my components, and they start with that composition that I explained to you. All right. So this is how fluids work. This is how you create a fluid. You always use fluids in sources. That's where you typically set up the fluid to be used within the simulation. There's only a handful of other models where selecting a fluid specifically ever happens. Almost 95% of the time, it's done in the source, and then that propagates from model to model based on the connectivity. Now, the next point of concern here when you're doing this is what happens when you have multiple fluids and you're trying to mix them together within the simulation. So let's create a copy of this fluid. And in this copy, the only change we're going to make, and we're making this change because it's going to help us with another point that I'm going to make in a minute. All right, we're going to change this to VLLE. Okay, so that's the only change. That's the only difference. All right, now we're going to take this. We're going to mix these two. Oops, that's not one. Mix these two lines together. So right now they're using the same fluid. So when I mix this together, everything's happy, right? Square and solved. If I put this fluid here, though, you can see the program's giving me a message here. It says streams with different fluid types should not be connected to the same port. Now, it worked out nicely here because I'm using the same components. All right, so everything was able to sort of work itself out, but the program is still smart enough to tell you, hey, this isn't a good idea. And the reason why I'm going to explain why it's not a good idea is let's take this one, put this one here. Everything blows up. All right, we have a different set of components in this line. All right, it's nitrogen, oxygen, water, than what we have in this line, which is our light hydrocarbons. So when it hits this mixer here, the mixer needs to know what to do with the two different fluids that are coming in and how to set the fluid coming out, right? So we're going to have a product stream coming out. What fluid is this product stream going to use, right? It can't use this because that doesn't have the components here. And it can't use this because this doesn't have the components here. And it can't just create a new fluid that has all of the components, right? So it doesn't know what to do with this, and therefore the program becomes unsquare and unsolved. If we look at this, it starts giving us, it says it's 10, add 10 specifications. That's because this is a small file. If I had more models, it would be way more specifications. You see an error like this that tells you to add or remove a ton of specs. That's usually an indication of some kind of setup problem like what we have here, right? Where we're mixing two different types of fluids. So this is a problem, and there's ways that we can fix this problem. All right, so the first way that you can fix this problem, and we're going to go back to this because I have it set up with the same component list. So in this case, we're going to switch from this fluid to this fluid before we get to the point where we're mixing. And the way that I can do that is by coming to the process tab, and I can add what's called a fluid change model onto this line. And when I come into here, I can tell it, I want the outlet fluid, meaning the fluid coming out here, to be equal to this fluid here. All right, so that fluid is this. All right, so now the fluid coming in, let's see if I can find fluid data in this. Yeah, of course, it's not showing me. Let me see this. There we go. All right, so model already rolled shows it. All right, the fluid coming in is the VLLE fluid, and the fluid coming out is the VLE fluid, right? Demo fluid. right? So it's switched from one to the other. So that's one way that we can handle this. All right, another way that we can handle this is, let's just say I'm going into a model now that does three-phase separation. So let's add that separator down. And so this model does three-phase separation. All right, and so when it comes into this model here, for it to properly perform three-phase separation, I would need to use a method that is VLLE. But right now, it's coming in as VLE. So I can come into my model, the separator in this case, I can go to Configuration tab, and there's a phases parameter. And what this allows me to do is it allows me to overwrite just for this model what the phase designation is. And so I can tell it, just for this model, do VLLE. Okay, so I didn't actually change the fluid. It's still VLE coming in here. It's going to do VLLE within the model, and then the products coming out are going to be back to VLE, all right, because that's what the fluid's using. All right, so this is a way of locally overriding just in one model. And you can do this in streams as well. You notice here's, or this is a source. You can do it in source. You can do it in a stream. All right, here's the same setting in the stream. All right, so this phases parameter appears in many different models. And it's a way of changing from one phase type to another without having to change the fluid. All right, so that's another way that you can deal with this concern. All right, the last way that you can deal with this concern, this touches on what happens if you're trying to mix different fluids that have different compositions, right? So this one here has these components, right? And when we were using this, and we'll go back to this just so, you know, the simulation is unhappy. It's using these components, right? So when it gets to this point where it's mixing flow, it doesn't know what to do with this because it's two different sets of components, right? So typically in a fluid change model, even if you use a thing that tells it use this other fluid coming out, you need to have what's called a comp model type parameter. So this is a change submodel that maps the components coming in to the components coming out. And so I would say the components coming in, nitrogen, oxygen, water, they equal to the components here coming out, methane, ethane, propane, isobutane. I do that in a submodel, right, like this, using equations. So I go in, I write equations that say, all right, the flow rate of water coming in is equal to the flow rate of methane coming out, for example. And I have to account for every component coming in and every component coming out. Now that's tedious, but it's something that you can do if necessary. The easier way to do this is just to define a single fluid that has all of these components, right? It would be a lot easier if you just had one fluid that used all of the components in the same fluid, right? And then in one, and just so you can see this, let me do that, okay? So this depth fluid here is, we're changing here. So we'll just go back. We'll just add the components. We'll just do it this way. Right. So if I add the components here, let's add N2. Oh, there it is. I have O2 and H2O. All right, so we'll add these components. Now that I have all the components defined here, what I can do is in source one here, I can define a composition that's just my hydrocarbon components and the rest of them are zeroed out. Just because they're there doesn't mean I need to use them in the fluid or in the source. All right, and then in the second source, I can define the composition to be just the other components. Right? So I can do this. All right, so whatever the compositions are for those components and zero out the other ones that I'm not using. So this is the way that you would end up doing it to make it easier so that you don't need a fluid change model, right? Now, if you think about this in relation to other software, other process simulation software, Most other process simulation software like Pro 2 or Aspen Plus, you go to a menu within the simulation file and you define your entire list of components, and that's used throughout the entire simulation. All right, and then you do the same thing with thermo, and that's used through the simulation, and you can pick, where you want to use certain thermo, but the component list is the same, right? And so you would define this list of components, but you wouldn't have the benefit of having a secondary list of components that you can define. It would be just a singular list. In Aviva Process Simulation, if you equate it to what we're doing in other software, we're basically going a level above that, right? Where you're allowed to create multiple groups of components in different fluid containers, right? And they're not linked to the simulation file. So any simulation file can use any fluid at any time, right? But because we can do any fluid to any simulation at any time, you still have to watch out for these concerns where you're mixing different fluids together, right? And so it's just a different thing that you have to think about that you didn't normally have to think about in other software. But if you want to take the approach of other software, you just use a single fluid throughout your entire simulation with all of the components that are used, and then you never have to worry about this concern. Right. Okay, so that's everything I want to cover with fluids. The remaining topic for the rest of the day is going to be related to the modes of operation. And so we're going to start off by going through an overview of what each mode of operation is, and then I'm going to show you a quick demo of concerns related to switching between the different modes. Okay, I don't know what that was. Wow, seems to be gone. Okay. Let me get the demo file open, and then I will start explaining. All right, so we're going to come back to our slides, and we're going to show a slide that summarizes each of the different modes that you can use as reference as I go through and talk about this. All right, so I'll make this full screen to make it easier to see. All right, so in Aviva Process Simulation, we use different modes of operation in order to simulate the types of calculations you would typically find in other software. So a lot of programs like Pro 2 and Aspen Plus are steady state simulation programs that are used typically to do design calculations. And so you're trying to calculate your heat and material balances, you're trying to calculate sizes of equipment, you're trying to do those types of calculations. Most of the time in those programs, you're using operating conditions like temperatures, pressures, flow rates, compositions, duties, stuff like that, that help you to accomplish those goals, heat material balances, sizings, etc. Right? So what we typically refer to this as in regards to how it solves and how those programs solve, we call this a flow-driven steady state mode of operation. So typically a flow is known at a source or a feed is known. That feed goes to a model that allows that model to solve, and that propagates and produces other products that go on to feed other models and allows you to continue solving. That's a sequential solving sort of behavior, but similar sort of concept even with equation-oriented software. When it knows certain conditions, it can solve certain equations first, and so it knows the flows typically, and so it can solve a lot of your mass balances related to known flow conditions. All right, and so this type of approach to solving flow-driven steady state mode is what we do in our process mode of operation. All right, so the very first mode that you start in. And we use this mode a lot of times to serve as the basis of how we build out our simulation. All right, so what you'll find a lot of times is that all the models are designed to be implemented, first used in process mode. When you drag and drop them from a model library and you put them on the canvas, the the idea that the program will be square and solved at its starting conditions, that all comes from the assumption that you're doing this in process mode, right? So we treat process mode as our starting mode to build out our base case, to build out the fundamental design that we're trying to simulate. Right? So this is the first mode of operation. Fluid flow mode is typically the mode that you go to next, and you transition from fluid flow to, or from process mode to fluid flow mode once you've got your base design finished. So you've built out your entire simulation, you've used these operating conditions that you've specified to calculate different sizes for equipment, and basically you've done your design. Right? We also refer to process mode typically as our design mode. Right? In fluid flow mode, we take that design and now we fix the conditions that we were previously trying to determine. So sizes that we were previously calculating in process mode, they become fixed conditions. All right. And we now free up the things that we were using to calculate that design, and we make those the calculated conditions. And so effectively what we do in fluid flow mode is we rate the equipment at the design that we just came up with in process mode. So we typically refer to fluid flow mode as a rating mode of operation. All right, now fluid flow mode is a pressure-driven steady state mode of operation. So it's still steady state, just the same as process mode. And in the background, the solver, the calculation engine that's APS is using to do the calculations, that hasn't changed. But specifications within your system are going to swap around when you switch to fluid flow mode. And because the specifications change to be different things that are specified, that's going to change the behavior of the way that the mode operates, right? So even though it's still steady state, it's still using the same convergence algorithms, all right, the same solver in the background. The fact that you have different conditions specified as your sort of starting points effectively dictates a different way of operating and behaving, the different way of solving, approach to solving the equations than what you had in process mode, right? So this is a pressure-driven steady state mode of operation. And to be pressure-driven means that you typically have known pressures at your boundaries. The source will have a fixed pressure, the sink will have a fixed pressure, and you need sinks in this case, right? And then you're going to have fixed sizes for all of your equipment. So valves are going to have CVs specified, pipes are going to have their diameters specified and their lengths. Equipment that has various sizing information like lengths and diameters and widths and so forth, those are all going to be specified. And for process equipment that doesn't necessarily have that information, what ends up happening is you have a lot of times calculated properties that serve as sort of like reference points for the sizing or the behavior of the model at a specific size, right? And so we have these reference conditions that tend to start to get specified and that your operating conditions reference back to. All right, so a lot of things get swapped around. And those operating conditions that I talked about before in process mode that you had specified to size your equipment, they now become calculated. So flow rates tend to be calculated. Temperatures, pressures throughout the system where pressures aren't fixed for some reason, they're calculated, right? A lot of times duties end up being calculated, right? So a lot of things flip around in terms of what's specified and what's calculated. And we're going to see that as we work through the rest of this module, this session today, right? It's mostly focused on what happens when you switch modes, why, and what you can do to help ensure success. All right, but on the most fundamental level, specs swap around, and that's what changes the behavior from mode to mode. The last mode is dynamics, and this is a time-dependent way of operating. And so when you go to dynamics, what happens is you typically make some kind of change, and then you run the simulation over time to see how that change that you made impact the behavior of the simulation. Now, normally you're going to start from a steady state solution. And given that this is pressure driven, just like fluid flow, you typically start from a fluid flow solution. And so you start in fluid flow, you have some kind of design that you're rating, and it's giving you a square and solved state. When you switch to dynamics, and if you just hit run when you go to dynamics, like we saw yesterday, nothing is going to change because you're already at a steady state from fluid flow. And that's good because that actually helps you to initialize your dynamic behavior, gives you a starting point from which that you can start from that you know is good, that you know is not going to cause you any problems when the dynamics is running, all right? Then you make a change. Typically, changes in dynamics are going to be set point changes and controllers, or some kind of process condition change like a boundary pressure, or some other type of model condition that you have the ability to adjust. Now, what you will find in dynamics is typically you don't have a whole lot of things that you can change or adjust yourself from a operating conditions perspective, like temperatures, pressures, flow rates. A lot of those things tend to be calculated. So the things that you do have control over tend to be the things that are controlled by PID controllers, valve positions, physical constraints of different pieces of equipment, stuff like that. Those tend to change the way that the dynamics behave. All right. The overall process that we typically see within the software is that you start in process mode, you build out your base case design. That gives you the sizes of your equipment that are adequate for the types of conditions that you are designing for. Right? Then you switch to fluid flow. Those sizes become fixed. Now you're rating those sizes on various operating condition changes. All right, so that way you can see, okay, if I did this in dynamics, would it still solve? Right? Does it give me a steady state solution if I change these conditions? Right? So you're rating how well your design worked out. And then you go to dynamics and you make those same changes. And instead of seeing the final values only, you now see how it changes from point A to point B for every change that you make. Right? And so you're more concerned about that in between behavior, which we would typically call the transient behavior, right? So what's happening between one steady state solution and another steady state solution. And then if you're happy with it, what you see, you can be done with the file, or if you need to redesign, you can switch back to process mode and you can come up with a new design, right? And that's the typical way that we see the software being used with these different modes of operation. All right, so with that said, I want to go over a couple of dynamic specific concerns, things and features that relate just to dynamics, so that way you understand how to use those. And then we're going to go into switching modes and concerns related to those. All right, so let me actually get another example file open. All right, so we have a very simple file here that's already in Dynamics. And if I come over here, we can see a little bit of it has already been run, and we can see there's some solution information. So we're going to come back and reset this and try to duplicate some of this work. So first thing you're going to notice is that when I come into the snapshots, I have a snapshot here called time 0. This is useful for a number of reasons, and I'm going to quickly explain that for you now, and then we're going to go on with the demo. So when you're in process mode and you're designing, you get a solution. When you go to fluid flow mode, you have another solution, right? And now you're going to dynamics. The solution that you're starting off with right here is the part that you were at when you were in fluid flow mode. Now you're going to run the dynamics and you're going to make changes. And so now it's running, you're going to make a change, and eventually it's going to come to a steady state and you're going to be done. All right. But at some point, you may want to come back to this solution, right? This state right here that we call our initialization state. And the only way that you can get back to this initialization step without going through this process that we just did, going from mode to mode, right, and switching over to dynamics, is to have a snapshot saved at what I would call time 0. That way, and I'm going to make a change so we can see our snapshot in use. Right, so we can see our values are changing. They're different from where they were when we started. Right. So now I want to go back to time 0. Right. I can come over here and I can revert the snapshot to get back, reset this time to 0, and get the results back to where I was when I started. All right. Otherwise, there's a button up here that says reset time to 0 and clear history. It'll reset this timer. It'll get rid of all this run history, but my solution state is still going to be where I'm at right now, right? It did not bring me back to where I started. So I want to be able to get back to where I started. It's a good idea to have this time equals 0 to get me back to where I started. All right, so good practice. Every time you switch to dynamics, take a time 0 snapshot. That way you have that starting point that you can come back to. That's just good work practice right there, right? Now, in dynamics, there are a bunch of different options that are available to you up here regarding how you run the simulation. When you first come over, it won't be running, all right? Unlike the other modes that run automatically, all right, you actually have to click a run button to start the dynamic run. Once you click run, it'll turn into a pause button to stop it, right? And you'll notice the timer is ticking up. So now it's ticking up over time. It's running. It's going up incrementally based on the time step value that is here. So you'll notice my time step is 0.1 seconds. What that means is that every 0.1 second of time, the program is solving the entire simulation and updating all of the information that's here. Now, it runs those calculations so quick that I don't actually see this tick up in 0.1 increments. However, those 0.1 increment values are being calculated and they are being stored in the background. All right, so it is doing all the calculations there. So effectively, even though we're seeing a little bit of milliseconds here and our seconds here, even though we see these things ticking up, 1 second at a time there, it's 10 points of data for every second that it's running, right? So we want to be careful with setting this value to a value that's reasonable for what we're trying to evaluate. All right, if we are trying to look at something in the range of multiple hours of running, 0.1 seconds is going to take us a very long time, right? Especially if we run it in real time to get all of that run information. I am just now hitting 1 minute in the run, right? If I needed to run this for 24 hours, 0.1 seconds ain't going to cut it, all right? Now, I could switch this over to fast. And what that does is it runs the calculations as fast as it can. And you can see it's ticking up nicely. Each one of these is a minute, right? So 25, 6, 7, 8, 9, 10 minutes. Like it's going up a lot quicker this way, but that's still going to take quite a bit of time to run if I'm running for 24 hours, for example. All right. So you have to work with this time step here to get the points that you want to evaluate and still make it so that the dynamic run is evaluated in a reasonable time frame. Okay. And the other thing about this fast setting is that it's only going to run as fast as your computer can handle. If you have a very large simulation with a lot of models and a lot of properties, right? Every one of these models, if you think about it, has all these different properties, all these different values that it's calculating. Every one of those increments is solving for every single property, right? So if you have a lot of models and it's asking for a lot of information in all those models, it's going to bog this down when it runs in dynamics. And it's going to take more effort from your computer to be able to run all those, right? So fast, even though it's pretty fast here, might not always be as fast as you hope it to be, right? It's only going to go as fast as your computer can handle. All right, so you got to work with these different items here, the time step, and in this toggle, excuse me, and this toggle to be able to set this up to run in a reasonable time frame. Okay, so the other thing that you're going to see up here is that you can run incrementally. If I click this run button, it ticks up on here one time step at a time. So that's also something that you can do. Now, I don't advise this unless you are trying to fine tune your run to a very specific point. So maybe I'm trying to get to, maybe I'm trying to get to 40 minutes, right? And so I'm running this out, and as I'm getting closer and closer to 40 minutes, I pause it and I start to just incrementally tick it up so I get it right exactly where I want it to go, right? So that might be one of the reasons why you want to do this. All right, but otherwise, this is going to be probably less useful than it seems. All right, you're generally going to want to work with the time step and just running either in real time or fast time to get to the time point that you're looking for. All right, another thing that you can do is you can solve to a steady state. All right, so let's make a change real quick. 75. Let's open up this trend here. We're going to talk about trends too in a little bit. So you'll see I'll set one of these up. Now, when I start to run this, you can see information changing here, right? And so the simulation is trying to run to achieve a new steady state. So this is trying to get to a point where it's matching this, right? And you basically want to get to a point where all these values stop changing. Now, this could take a long time. If I let this run out in real time, it could take quite a while. Even at fast time, depending on what it is that the change is, it might take a long time before you stop seeing numbers change, right? So one of the things that you can do, and I'm going to have to make another change to see this, right? One of the things that you can do is you can instantly solve the simulation to the steady state solution, right? So right now it's running. So eventually we'd get to maybe let's there you go. So eventually get to like a steady state solution, but I don't want to wait that long. So I click this, I say solve the steady state. Bam. Now it updates the values that are here, what you're seeing. And when I click run again, it's instantly jumping to the steady state solution. It's not a great example. I didn't see much of a change. Let me make them another change real quick so we can see a larger change in this. So we can see where these values are right now, right? This is where we're going and this is where we're at. If I solve the steady state and now I run, you can see it instantly jumps straight down there, right? So it brings you right to the steady state solution as if you're making this change in fluid flow, right? Fluid flow is a pressure-driven steady state solution. So this button is basically invoking a fluid flow solution, right? But it cuts out all the run history. So you don't know how it got from here to here. It just got from here to here, right? So it's nice that you have this capability, but it's not always going to be as useful as it seems. It just depends on what it is that you're trying to accomplish with your dynamics. Okay, last couple things about dynamics specifically that I want to talk about. You can take dynamic snapshots with run history. So maybe if I wanted to, I could take a snapshot right now, trying to not overwrite one of these. So give me a second to see if I can get, all right, there we go. Right, so I got a new dynamic snapshot here that I just took. And when I took it with this icon here, instead of this, which is the one on the toolbar, you could see a little indicator here that says that it has solution information in it, has calculation run information. And so when I revert to a snapshot with run history, it brings me to that final solution state and has all of the run data in it. Right, so this is a great way to be able to get all of the information for the run back. Right, however, when you have a snapshot with solution history, that's going to store a lot of information, right? Because every single time step is another solution for the entire simulation. So when you start to have dynamic run history that's being stored and or snapshots that store that dynamic run history even further, you are going to get to a point where you're going to bloat the file size, right? Let's go over here and save a copy of this file. Come back. You can see this simulation file is 11 megabytes in size. Now, this is a very small file, right? So that's not a lot of information that's trying to save. So 11 megabytes isn't terribly large, but even 11 megabytes could be difficult for some email servers to be able to send via email, right? And if I had a larger file with a lot more information, you can imagine this is going to be hundreds of megabytes in size. I have actually seen customer files that are gigabytes because of snapshots that have run history stored in them, right? So you always have to be careful how you're saving this data because it's going to bloat your file size significantly. And one of the things you can do to reduce this size is you can send it to a zip file, right? If you zip it up, you'll see, oh, this isn't going to show me it here. Let me, there we go. If you send it to a zip file, you can see it compresses quite a bit. So this is one thing that you can do if you absolutely need to store this information, right? You can zip it up and that'll compress it down quite a bit. But even then, if it's really, really large, it might not be able to save all of it. One of the things you can do is you can flush the snapshots and get rid of the calculation history, but save the final state of the snapshot. So if I flush this snapshot, so no more run history, and now I revert it, it still shows me the timestamp. It still shows me the final values, but there's none of that information prior to this, right? So it's getting rid of all that extra information that I don't need. That's taking up more file size, right? So that's one of the things that we can do is flush it out. The other thing that you can do is there's an area here called the History Manager, and this defines what points of data are stored within my dynamic run history. And so it works between this multiplier, which goes against the step size, as well as the number of points that I have defined here to give different ranges for different sets of collection information. Now, there's different sets because typically we are more concerned with run history in the initial phase of the dynamic run when we first make a change to the steady state solution. And so we typically save a lot more points initially over a smaller time frame. This is 300 points over 30 seconds. Whereas this has more points, but it's over 570 seconds. Yeah, I don't know why I blanked on that for some reason. Sorry about that. 570 seconds, right? So this is more points, but they're over longer time increments, right? So it spreads out the points more, right? So these different collection sets are designed so that more information is saved initially, and then as you run, it saves fewer and fewer information over time, and then eventually it gets to a point where you're beyond the last time range here, right? And so anything beyond this point is just dropped. And so you don't save that information anymore. So what you can do is you can work between these, setting different multiple values, different number of points, and different step sizes up here to change what information is saved. And that'll also change how much information is stored in your calculation history. So that's another thing that you can do with these different files. Okay, so one last topic for dynamics, and then we're going to talk about changing modes. If you want to create a trend, which is a way of visualizing the change in specific results over time, you come over here, you go to the tools, drag a trend icon onto the canvas. And when you first open it, it's going to be blank. And you can set it up manually through this configuration area. But the easier way is to find the properties of interest and drag and drop them onto the trend icon. All right, so I drag and drop the pressure, and I drag and drop the temperature. And so now I have those being plotted on this canvas. And I can come in here. I have configuration options. I can make one of them on the right axis instead. I can change the colors if I wanted to. I have different options available to me here. And then when I run, I can see my information being plotted on the curve. All right, and so let's run it out. And so it's at steady state, nothing's changing. Let's make a change. Right, so I can see my trend being populated. Right, so this is one of the things that you can do with the software to visualize dynamic results changing over time. Okay, so the last topics that we're going to get into here for the day are what happens when you switch between modes. And we're going to use this example to help set us up on that discussion. I've told you before when I was talking about the different modes that when you switch from one mode to another, the main thing is that the specification status is going to change between the different models. So every model in the software has certain conditions, right? Flow rates, temperatures, pressures, whatever they are, that are either specified or calculated by default based on the mode they're in. When you're in process mode, for example, this source model has the flow rate, temperature, and pressure specified. Now, this is a cooling water example, so there's no composition, but that would normally be specified as well, right? The sink has everything calculated. This is the default behavior. And then I have two models here, and we're going to talk about why. But one, they're both pressure loss models, effectively. So a valve and a pipe, right? They're going to model our pressure change. All right. In the valve, we have the pressure drop specified, and it's calculating the CV. And in the pipe, we have the velocity specified, and it's calculating the pipe's size. Now, you notice this is a parameter. All right, so the parameter here is set to what's called next larger MPS. We're going to get into why in a minute, right? But this is not actually used while in process mode. It's calculating the size. And so the value that's calculating is this, D, which is the actual diameter. All right, so this is the actual diameter that's being calculated. And that's what you see here on the canvas. All right. When I switch modes, these specs are going to swap around to support the purpose of the other mode. Right. So in process mode, we have a known flow rate. We have a known pressure. We have known pressure loss or velocity in these models. And these are being used to help us size, in this case, the valve CV or the pipe size. What diameter do we need, right? When I go to fluid flow mode, things are going to swap around because now it's not going to be trying to calculate these sizes. It's going to fix the sizes. And it's going to specify the boundary pressures and free up the flow rates. So we switch, then we can see flow rate is calculated. Pressure at the sink is specified. And for the valve and pipe, CV is specified and diameter specified. It's technically this size parameter that's specified, right? And instead of the things that were specified before, flow rate and pressure drop and velocity, those things are calculated in this case, right? So switching modes is going to swap around the specs, right, to meet the purpose of the mode. In this case, rate our sizes that we previously calculated, right? However, one of the things that you're going to notice is that when I switched modes, when I went from process mode to fluid flow mode, my results changed in this network down here. All right, and I'm going to explain why specifically for the pipe, but generally what happens is we should expect our specs to swap around, but our values not to change, just like we had in this upper network. But that's not always going to be the case. Sometimes our values are going to change, like here, and typically it's going to become, it's going to be because of mode specific equations that are used within these models. Every model is defined in a certain way where there are conditions in the models that can trigger different equations being used for different calculations depending on the mode we're in. I'm going to give the most basic way of understanding this that I can. All right, but you got to understand that this goes across all different types of calculations across every model. All right, so let's take mass balances. The equation that we use in a steady state mode of operation for a mass balance is that everything coming in is coming out, right? If we factor in all of our assumptions that we make about steady state operation, the mass balance basically reduces down to just in equals out. And that's our mass balance, right? But when you do dynamics, right, that's a time dependent phenomenon, you can't make that assumption. You have to also include the possibility that there's accumulation in the unit or that there's loss, like a leak or something, right? So those additional aspects need to be accounted for in the mass balances. If we think about it here in the terms of the software, when you're in process mode, your models have certain equations that are being used that are based on certain assumptions that we can make because we're operating as a steady state sort of operation. But when we go to something like dynamics, and remember, fluid flow is a precursor for dynamics, they share the same default specs. So even though this is steady state mode of operation, it tends to use a lot of the same equations that are used in dynamics, which are much more realistic. They take into account more factors than we would normally do in a normal flow-driven steady state operation, right? So when we come to fluid flow and dynamics, the equations now have to account for the potential of accumulation and loss. And so it's a different set of equations, and that can change your results depending on the potential situation that you're in your file. Every file is different, right? Now, for this specifically, with the pipe, remember I said before, the pipe size is set to be the next larger NPS, nominal pipe size. And so it's calculating an actual pipe size, but this actual pipe size isn't a real nominal pipe size. So what ends up happening is it needs to use the next largest nominal pipe size, which is a 2-inch pipe. That equates to a 2.06-inch pipe as opposed to 2.03, right? And that larger pipe results in a larger velocity and a larger flow rate going through the pipe, right? So that's why the results change in this lower network. Right, so you can see just a couple examples though of what I was saying between the mass balances and this, how results might change. And so when you switch modes, what you should expect to see is that your specs swap around to support the purpose of the mode. What you might also see though is that your values change. And so one of the things that you want to make sure that you do is that you take snapshots before you change modes. If I come up here, you can see I have a couple of snapshots taken. I can also see that the program is smart enough to take an automatic snapshot in the mode we were leaving. So, right, so if I am in process mode, I go to fluid, it takes an auto pro snapshot. All right, let me do that again actually and delete this so we can see it. Okay, so I go from process mode, I go to fluid flow mode. takes an auto pro snapshot. And so what's nice is if I come back to process mode and I revert this, I can get back to where I was, right, before I switched. Right now, it only takes this auto snapshot when it switches away from a mode that is solved. So it only take one per mode and only overwrite it when you're switching from a solved state. So you never have to worry about this being from an unsolved solution. So that's useful, right? However, it's still to your advantage to take your own snapshots before you change modes. And I'm going to show you why. All right. So one of the things that happens when you switch modes and your results change like this, right, is that when you come back to the old mode, it's not automatically going to give you back the results that you had. So this was 50,000 pounds an hour. It's not automatically going to give me 50,000 pounds an hour back when I go to process mode, right? And the reason for that is because the program is attempting to retain the same solution every time it changes modes, right? So even though it changed initially when it went from process mode to fluid flow mode, it's still trying as much as it can to keep the solution. And so when you change back from fluid flow to process mode, it's trying to retain that solution. All right. It also wants to assume that, you're happy with that solution, that that's a solution that you desired. And so it wants to maintain that when it switches back. Right. And so when I come back here, my results have changed. Right. And I use that auto pro to get me back to where I was. However, let's take this one more time. If I switch back to fluid flow now when I come back to process and I'm at this other solution, if I use that auto pro snapshot, nothing happens, right? Because I have swapped one too many times between the modes. The last time I swapped from process mode to fluid flow mode, I was at this solution and it overwrote my prior solution that I was counting on to get me back to where I was. So that's why it's important that you always save your own snapshot that you can come back to. All right, so now I have this pre-mode swap. I can come back to where I was before I changed modes. Okay. One more thing that I want to mention about changing modes in terms of behaviors within the file is that if you are in a mode where you've swapped around specs like this, right, and they're no longer the defaults, right, because normally this is calculated and this is specified. When I come back to the mode, it's going to do its best all the time to retain your user changes, right? So it knows that I had this defined this way before. It's going to work to keep it that way when I switch it back, right? When I come back to that mode again. All right, so notice it retained this change. That's always something to keep in mind. One more thing that I want to talk about this icon and these colors that you see within the spec box. Right, when I come into the mini inspector and I look at the various colors and things for these different spec boxes, I'm going to notice a couple different things. If a box is white, whether it's calculated or specified, it doesn't matter. If it's white, it means it's at its default for the mode you're in. If it's blue, it means it's a user change that is away from the default of the mode, right? So this is normally specified. This is normally calculated in process mode. Because I swap these around, the boxes are blue. Both of them are blue. If I have boxes that are red, those are candidates for resquaring the simulation. We talked about that yesterday. However, you will also see occasionally a box that's blue and red. This is not anything that you should be, confused about. It's as simple as it sounds. It's just a box that is a candidate to resquare the simulation that was changed from its original default status. Normally, this is calculated, but because there's a check here, it's a user-defined change, that's away from its default state. Hence the blue. It's also red because it's a candidate to resquare the simulation. Right, so that's just indicating both of the normal coloring to you. Right, it's not anything special beyond the normal colors, what they mean. All right. One last thing I want to point out here. If you right click up on the simulation name, there's an area for changed specifications. And this window is going to show you every single variable in your simulation that has a blue checkbox, meaning a change away from the default state of the model in the mode you're in, right? So these things are normally the opposite of what they are right now. This is normally calculated. This is normally specified while we're in process mode, right? This window will change depending on the mode you're in, right? Because every mode has a different set of defaults, right? So you can use this to your advantage for a lot of reasons. One thing that you can do is that you'll notice there's a thing that says set here, and it says set 1. Let's make another swap real quick. Let's do this. This is now set 2, right? These sets tell you what variable you swapped with one another. So I specified this and freed this up together. That's one set. I specified this and calculated this together. That's another set, right? So these are things that the program is telling you as part of this window, right? These are swapped together. The other thing that this window is useful for is convergence troubleshooting. Any deviation away from the default specification state is going to potentially create more complications for the way that the simulation solves. Each one of these modes is designed for specific types of conditions to be specified. And so if you start swapping things around that go against the intent of the mode, it makes it harder for that mode to solve. And so when you have a failed solution, if you come to this window, you can review these and look for things that seem out of place, right? I'm in process mode. If I look at this and I review these and I'm unsolved right now, I might say, oh, that's weird. Sink pressures aren't supposed to be specified in process mode. Source flow rate is typically specified in this mode, right? These are things that are going to stand out to me as potential problems. And so I could use this window to review what has been done in the file and potentially find an error in the way that I have it set up. This is actually a lot more useful than it might sound in my little quick explanation. And normally in a full training class, I would pull out a demo that shows me troubleshooting a customer file using this. All right, so this is a very useful capability to be able to troubleshoot your convergence. One very easy thing you can keep in mind is that if you revert all of these back to their default, you are very likely to be square and solved, right? In many cases, right? Depends on how far you deviate in terms of the values, right? Because again, this program's designed, especially in process mode, to be square and solved at its default state, right? The default conditions that are specified, right? So that's a design intent of the software. All right, so there's a couple more concepts we want to talk about real quick right before we finish for the day, and they're still related to transitioning modes. Let me get a file open real quick and show this next one. All right, when you switch modes, sometimes one of the things that you might find happen is that the simulation becomes unsquare and or unsolved. And the reason for that could be a bunch of different things, right? And as you can see from here, there's a lot of red, right? A lot of these boxes are red. A lot of these models and streams have red circles on them, red X's. It can be difficult to figure out what's going on here. Even coming up here and saying, oh, it says add 2 specs, remove 2 specs. I could go through that, right? I can go through and try to add and remove 2 specs each and see if it's square and if it's solved when I do that. But it's very likely that if I'm coming from process mode and I'm square and solved, and I switch to fluid flow mode and I'm not square and solved, I need to do something more with the file to prepare it to switch modes, right? And so now what I want to do is I want to try to get this simulation prepared to switch to fluid flow mode. And the first thing I'm going to want to do is I'm going to go into any model. Just about any model has this. And there's a parameter called mode check. It's a global parameter. If I change it here, it changes it for every single model in the simulation. And you're going to change it from process mode to all modes. And what this is going to do is now every model in the simulation is going to start to flag warnings that help you better understand what you need to do to transition from one mode to another, transition from process mode specifically to fluid flow and dynamics. So if I hover over this warning for the header, it tells me I need a flow calculating model in each inlet stream, such as a pipe, a valve, or set the stream's flow resistance, which means going into the stream and adding in a resistance, right? Like this. This is an arbitrary pressure loss resistance that you're adding in, just so that there's something factored in there. All right, we're not going to do it that way. But we're going to go the route of the valve, right? But you can add any one of those three things to account for that warning. And then the other one tells us we should balance our pressures. Normally, in process mode, you don't have to balance pressures for models that mix flow. It just takes whatever the lowest pressure is coming in. So if I look at this header, the pressure of the header is equal to the lowest pressure coming in. Let's change this. Right? So I have 55 kPa or 5,500 kPa in this line, 5,000 kPa coming in this line. It takes the 5,000, the lower of the two. I don't know why it's 5,000.08, but let's make it round. All right, so it takes the lower of the two. That's what it does by default in process mode, anywhere where it's mixing flow. All right, now we're going to talk tomorrow more about this concept of inlet pressures and balancing pressures. But one of the things that you typically want to do when you're changing modes is balance your pressures. And so you'll see me do it here, but I'm not going to go into the detail of it right now. Right. So let's start by addressing the first message about the flow calculating models. So that just wants me to add some valves or pipes to each one of these streams or flow resistance in the stream. So we're going to take some valves and we're just going to drop them on here. All right, so bam, that's taken care of. We're going to notice down here for the sink, it has the same, same message, right? So we're going to also add that here as well. And that's going to get rid of that warning. Now, when I look at this warning, it's just talking about balancing the pressures. So I can come over here. I can set this to balanced. When I do that, I become overspecified because I need to free up something to allow one stream to balance into the other. So I do that. So now the message is gone. Right? And now I've accounted for all of those mode check warnings. If I switch, beautiful, solves just fine. Square solved, no problems, right? Because I have now taken into account all of the factors that it needed to account for in order for it to solve properly in this mode, right? So one of the things to keep in mind, and even though the messages are going to tell you these things when you turn that global mode check message on, is that fluid flow mode and dynamics are much more realistic ways of operating. You have to account for everything that you would normally make assumptions on while in process mode, right? So if you're trying to think about what things you need to do to prepare yourself to go to fluid flow or dynamics, think about the way things would operate or work in a realistic manner. And that's going to help inform you on the things you need to do to get your file ready to transition modes. All right. I do have these slides here that talk about some of the other types of messages you might see, such as not having an outlet stream connected, not having both sides of a heat exchanger connected, not having a sink. Sinks are required in fluid flow and dynamics, right? So that's something that you're going to need. Making sure your pressures are balanced. Handling zero flow or pipes, because with a zero flow going through a valve or a pipe, it can't calculate the size like the CV or the diameter in process mode. And so you need to take steps that the warning message will actually tell you what to do to account for those things. Other messages are also possible. The most common one that I don't have listed here is if you have a drum or anything with some kind of level in it, you typically want to add in level control before you switch modes. So put a PID controller on, connect it to the level fraction, connect that to a valve. That way, the level in the drum, that's another thing that will commonly come up as one of these warning messages. Right? But you want to make sure that you do this in order to properly transition from one mode to another. Surprisingly, I'm ending right on time. Pretty much covered everything that I was hoping to cover today, which is good. So let's go up to the top and talk about what's in store for tomorrow, and then we'll do a little bit of Q&A. So tomorrow we're going to be talking about model library management, which is the idea of how you work with model libraries as a whole. All right, so each one of these different tabs here, creating your own libraries, importing libraries. I'm going to talk about some libraries that exist that aren't already incorporated into the software that you might want to use. All right. I'm then going to move on to individual model concepts. And so you saw one today. I talked about this concept of balancing pressures, right? That's one of the topics we're going to get into more detail about tomorrow. But there are other individual model concepts that we want to talk about that are going to help you with your use of the software. Right, and then we're going to get into three specific types of model, well, two specific types, and then one specific model library that you guys are going to end up using in this academic competition. So we want to make sure that we cover those in a little bit more detail, so that way you're prepared for using them within the academic competition. You're also going to find a little bit more model discussion, which is basically all we're doing tomorrow in sessions 4 and 5. So on session 4 on Thursday, we're going to talk about the economics model library and all the models in there. And then on session 5 on Friday, we'll do reactors and columns, which again, this is an optional session for this year's competition. But if you would like to learn about those, I suggest you attend that session. You'll learn a lot more information about them. Okay, with that said, let's open it up for Q&A.
Yeah, we have 3 questions that I didn't answer. I let them to you. So I will copy here again because there was some conversation. So the first one is there.
Okay, someone had asked about not being able to see the full table that I had up, but I think someone answered that for them. The dynamics mode can be used to study the startup behavior or only the study behavior of the system between some limits around steady state. Meaning, what he means is a disruption in steady state. So you're already at a steady state and then you make a change and then you get to another steady state. So typically the dynamics mode does the disruption in the steady state. You could work in some ways to do startup and shutdown, but there are very specific concerns when it comes to startup and shutdown in dynamic simulators, and the normal dynamic operation with the process model library and many of the other model libraries doesn't really do the full scale startup and shutdown. Right? We do have a batch distillation library, which by its pure definition being a batch operation is going to have a definitive start and end. And that does start up and shut down for that specific process. But it's the only one where that is more all encompassing. If you're going to do startup and shutdown of the other systems within the software and the other model libraries, you kind of have to work within some kind of limitations, right? Like you can't have a true zero flow startup and then start ramping it up. You might have to start with something that's small and not zero, and work it up from there so that it can have something already in the system going, right? Same thing with a shutdown. You're not going to be able to bring it to complete zero flow. You're going to bring it to some very small flow instead, right? And then you're going to have similar considerations and constraints with other properties, right? So that's sort of the idea there with the limitations of a real startup and shutdown in Dynamics.
Great. There are other two questions I am copying here in the chat because we lost in the conversation.
Okay. Yeah, that's the. So I see a question about the competition. I assume you answered that one already. Is it possible to see the equilibrium data for the mixture defined in a custom fluid as a table or a plot? Yes. So if you go to your fluid, oh, this is not a good file for that. Let me get a file with a fluid open, or actually I'll just open a normal fluid here. All right, so if you go to a fluid, all right, this one should have information. There are two different sections where you can get either component or thermo related information. And so there's the component data section, which is going to give you component property information that are either constants. So, and it's broken down by different categories of values, right? So here's some basic properties, right? Molecular weight, boiling point, gravity, right? There's some critical properties, heat formation information, so forth. And then there's temperature dependent properties, right? So if you go to vapor pressure here, you can see the vapor pressure correlation and its information, and you can even plot these things, right, into a plot. All right, so this is for component-specific properties. Now, the question is more for thermo-related properties. If you come to the method data area and you click on the button for the method, the thermo method that you have selected, you're going to see a table here of all of your binary interaction parameter data that the program has in this, in its database, right? So again, we talked yesterday on the advanced tab, there's the TDM application. That's what's storing all of our component and thermo data. It has all the same information that you're seeing here that I'm showing you right now. All right, but this is stored on a global basis, right? And so it's going to be for everything within the entire simulation. Whereas you're just looking at properties for these specific components and for these specific components with this thermo method in this fluid, right? But if you wanted to see everything, you would go through TDM to see everything on a larger basis, right? But if I click on any one of these, I can see what the binary interaction parameter data is for these. And in both areas, I have the ability to overwrite the properties that are in these tables, right? So I could change the interaction parameter data. I can change component property data. And for components that have missing binary interaction parameters, I can provide them, right? So this pairing here with SRK doesn't have any data. So I could go through and populate that data here. All right. Hopefully that answers the question.
Yeah, there is another one.
Yep. Okay. Does Aviva process simulation support equation-oriented modeling? This is an equation-oriented simulator. All right, so it's by definition, it supports it. If you're asking about custom modeling, that's what we're going to talk about on Friday as a optional session. You do have the ability to create your own custom models where it is a bit effectively equation defined. There is a structure. You don't need to know any coding in order to do it, but there's a structure, a window with different sections and different ways that you need to put in the information. But effectively, what it boils down to is writing equations. I pick just one of these models real quick. Just take the drum. there's a section and you write equations, right? So it's equation oriented, and you write it in whatever format you have for the equations, and the program interprets every single equation that it's using within software and can understand the equations, understand the relationships between equations through use of common variables. And that's really the fundamental basis for how it knows how many specs you need to add or remove when you're swapping specs around, right? Or when the simulation's over or under constraint, right?
Okay. I had one more question.
Yeah. So it looks like there was a clarifier to that equilibrium question. Is it possible to calculate mixtures like 30%, 30 mole percent potassium hydroxide and lye as a predefined fluid, or do mixtures like that have to be defined in a custom fluid? So the 30% part is the composition, right? And the other components are just the components, right? So you can create a fluid that has those two components and set the starting composition equal to that percentage, right? And then when you use it in the software, you'll get to see how the equilibrium calculates within your source model and your streams and so forth. Or you could set some other starting composition, and then in the source, you can always override it with this specific composition value. It just depends on which way you want to go about it. But the actual equilibrium results in terms of what it's solving for the temperature or the pressure at this condition, that's going to be in the simulation where you're using the fluid at the conditions that you have desired, right? It's not going to show you that in the fluid itself. The fluid is storing your equilibrium data, like your binary interaction parameters, and it's storing what components are being used, but the actual integration of the thermo being performed is done within the simulator, right? And then there's also, we don't talk about it in this training, but if you go to the tools menu up at the top, go to the tools menu, there are other thermo-related outputting capabilities that you have here that can link to the fluid, such as BVLE calculations, binary curves, and tertiary curves that you can create, right? Ternary curves. Right? And you can also do phase envelopes. So you have these capabilities that can link back to the fluid without actually having to use the fluid in terms of in a source model. You can just pull these and connect them to the fluid, set the conditions that you want to evaluate, and they'll spit back different results depending on the type of plot or capability that you're using. Okay. So solubility of solids in water or other fluids is included in the fluid models. Okay, so solids are handled in a special sort of way within the software. We don't have equilibrium with solids. So when you look at a fluid, and let's actually take I'm going to show you an electrolytic fluid, so that way you can better understand and appreciate this. So let's just look at this one. Should be fine. All right. So this one actually uses ionic components that aren't defined necessarily as solids, but this is probably not the best example. Let me see if I can find an example that has a solid component in it. Or I might just have to create one real quick. Seawater? No. I'll just open a file and create one. Just give me 1 second. I don't want to disturb any of the fluids in the libraries here. So I'm just going to create one from scratch. Actually, I'll copy one and then I'll do it. Okay, so let's say I add a known solid component to the simulation or to the fluid. All right, so I can come into my list here and I can browse for something like, I think carbon is an option. All right, so carbon is obviously a solid component, right? When I add it to the list, right, by default, the program doesn't do anything with it to show me that it's a solid or designated as a solid, and my phases are still set to VLE. So if I try to use this component in my fluid, in my simulation, it's going to give me problems, right? It's going to give me errors because it doesn't know what to do with this component because it's not actually a vapor or a liquid component. So it's going to have trouble with the equilibrium calculations. So what we do is we check this box, include non-equilibrium solid components. And you notice it's under the phases section. When we check this box, we are telling the software that anywhere this fluid is used, if there's a solid component, use this solid component as part of it basically travels with the liquid phase, but don't use it in any equilibrium calculations. It's just there, right? It's not actually partaking in any equilibrium calculations. And so now when I come down to this component list, you can see it's designated this as a solid component. And if I wanted to, I could also designate other things as solids if it wasn't already designated. All right, this one already has it checked. And so now when I use this, let's say I send this fluid to a drum. Throw together a quick little example here so we can see this. Okay. So we still have this. Let's add some water and our solid. All right. So when this goes into the drum, right, the drum has to perform a separation. Vapor goes overhead, liquid comes out the bottom. So it'll do the rigorous thermodynamic calculations between these three components, nitrogen, oxygen, and water, to calculate what goes overhead as vapor, what goes out as liquid, right, at the conditions that we have specified. But carbon, it just ignores, right? It just says it's coming in and it's just going to go out with the liquid. So when I look at the results here, we do have a little bit of water vapor here. You can see that, a little bit of water vapor, right? When we look at the results here, right, all the carbon just comes out with the liquid phase, right? It doesn't have an impact on the equilibrium calculations within the simulation, right? So that's what it means to be a non-equilibrium solid component. Now, if you want to include the solid component into some kind of phase consideration, then what you can do is you can create a reaction submodel that tells it through equations in the submodel how to utilize the solid in relation to other components, how to perform some of these equilibrium calculations, or reactions, for example, like how to react it away or form it from other components. And then down here in this models section, you can tell the program, tell the fluid to use that reaction submodel to perform that reaction, equations, whatever the equations are, wherever this fluid is utilized. And so then in the source, in the streams, in the drum, in the sinks, right, the equilibrium based on your reaction submodel would dictate what's going on with the solid component and whether it, transitions to a different phase or reacts or in any sort of way or is formed in any sort of way. That's all dictated through this reaction submodel. And when we talk on Friday about reactors, you'll see how we can create a reaction submodel. Just as another quick example of this, we come back to this electrolytes fluid. There are a bunch of reaction submodels down here that dictate how the electrolytic reactions occur, and they're used in these fluids, right? So if I come into this one here, this has the components in it, right? And there is a thermo method called, well, in this case, it's Wilson. I was expecting the electrolytic NRTL, but it's Wilson. It's used, right? But the actual electrolytic reactions are being calculated through this submodel here, right? RX HCl BE, right? So that's this here. And this is what's actually performing the electrolytes calculations. So here's all the different equations that dictate how the electrolytic behavior occurs, what's dissolving, what's forming, and so forth. The fluid just takes into account all the potential species involved in this reaction. So it's a little bit more in depth about solids and solids handling than I was planning on getting into, but hopefully that was useful. Are there any other questions that I can answer?
Okay, so if you don't have any other questions, tomorrow at the same time, same link, hope to see you here again. Thank you everyone to join us, and thank you again, Richard, for share all those information with us.
You're welcome. And real quick, session 5 will be recorded on Friday. A big reason why we are doing a session 5 is because in the future, if there are academic competitions that require the use of those topics, we don't want to have to re-record at a later date. So we are adding the optional 5th session, so we have it in conjunction with all of these other sessions that we are already recording.
Yeah, perfect. Thank you.
Thank you, everyone.
Bye-bye.
See you all tomorrow.